Welcome AXOR, Galactic Observatory. Tonight, the journey drifts into one of the darkest and most fascinating corners of the universe, the hidden secrets of the stars. These distant lights may look calm and beautiful in the night sky, yet behind their quiet glow lie stories of immense power, collapse, destruction, and creation. Some stars grow so large they could swallow worlds. Some die in explosions that reshape galaxies. Others collapse into strange remnants that spin, pulse, and bend the laws of matter itself. In this slow and relaxing documentary, the story moves gently through the terrifying truth behind starlight, from giant stars and supernovae to black holes, neutron stars, and the fading future of the cosmos. If this kind of peaceful space journey is something the viewer enjoys, please like the video, subscribe to the channel, and share a thought in the comments. Now the mind grows quieter and the stars begin their story. Far beyond the familiar patterns of the night sky, stars exist first as distant events in darkness, scattered across immense reaches of space that no human sense can naturally grasp. They do not begin as individual objects in immediate detail, but as points of light separated by such extraordinary distances that even their brightness hides their remoteness. A star seen from Earth appears small and steady, yet that appearance belongs more to distance than to nature. The light arrives only after crossing gulfs so large that ordinary measures lose meaning. It travels for years, centuries, thousands of years, and in many cases far longer, before reaching the eye or the lens that records it. In this way, every star seen at night belongs partly to the present and partly to the past. Some shine from nearby regions of the Milky Way, while others belong to remote populations so far away that their light begins its journey before entire human civilizations rise and vanish. A quiet sky therefore contains a hidden archive of time. The starlight does not simply reveal where stars are, it reveals when their light leaves them, and that difference between event and arrival introduces one of the first unsettling truths about the stars. They are never seen exactly as they are. They are seen as delayed signals, old messages carried through a dark and nearly empty medium that offers little resistance but never grants immediacy. Even the nearest stars stand at such remove that presence becomes a kind of illusion. Distance turns every view into memory. The sky appears still because the scales involved are so vast that change usually escapes notice. But the stillness is only apparent. Stars move through galaxies, rotate, brighten, fade, erupt, expand, contract, and in some cases die, all while their earlier light continues outward. A quiet point in the sky may already have changed profoundly by the time its light reaches Earth. In some cases, the star may no longer exist in the state that produced the light now arriving. Its outer layers may have shifted, its temperature may have changed, or its life may already have ended in collapse or explosion, while its earlier radiance continues to cross the dark. This gives the sky a strange quality of survival. A star can remain visible after the event that destroys it, not because the star persists, but because the light does. What seems enduring may in fact be a lingering signal. What seems present may be absent. The universe allows this delay everywhere, and so the night sky becomes a place where existence and appearance do not always match. The farther outward observation moves, the more this truth deepens. Remote stars are not simply far away, they are far back in time. To observe them is to look through layers of cosmic history arranged by distance. Nearby stars offer relatively recent light, while distant ones reveal earlier chapters in the life of the universe. This outward view shows that darkness is not empty. It is a vast interval filled with travel time, with silence, and with the slow movement of energy from source to observer. The darkness between stars is so broad that even light, the fastest known messenger in nature, requires long spans to cross it. That fact gives every star an air of isolation. Each one burns within its own region, pouring light outward in all directions. Yet most of that light enters emptiness, racing through enormous voids where nothing sees it and nothing answers. A star may shine with extraordinary power, but its brilliance does not remove its solitude. It sends its radiance into a universe where separation is one of the defining conditions of existence. This outward perspective also changes the meaning of brightness. A bright star in the sky may not be the most powerful star, only one that happens to lie relatively near. A faint star may be dim by nature, or it may be magnificent and simply very far away. Appearance can therefore mislead at the most basic level. The eye ranks stars by visible brightness, but the universe does not. Some of the most luminous stars known stand at great distances and appear modest, while some nearby stars dominate the sky mostly because they are close. This gap between appearance and reality gives the stellar world a hidden structure that only careful measurement can reveal. What seems obvious at first glance often turns out to be incomplete. The stars invite wonder, but they also resist simple reading. Their light must be interpreted, corrected for distance, and understood as evidence rather than direct encounter. From the outermost view, stars are therefore both familiar and unreachable. They are the oldest visible companions of human life, yet they remain physically beyond all ordinary contact. Their light falls across oceans, deserts, forests, and cities with a calm that suggests intimacy. But that intimacy is false in literal terms. The nearest star beyond the Sun remains at a distance so great that modern travel methods would require spans far beyond a human lifetime to approach it. Even the local stellar neighbourhood is almost entirely inaccessible in practical terms. The stars seem to decorate the sky, yet in reality they occupy a three-dimensional wilderness of staggering depth. They do not hang from a surface. They are distributed through enormous volumes of space, with darkness between them so extensive that the mind struggles to hold the scale steady. This is where the terror begins, not in violence or explosion, but in remoteness. The stars are not close lamps in a dome above the world. They are far suns scattered through a universe whose size exceeds instinct at every step. Their light reaches Earth as a mercy of physics, but that same physics declares how distant they truly are. Seen from outward space, before any one star is studied in detail, the stellar realm already carries its deepest secret. The beauty of the sky depends on distance so vast that every point of light is an island, every gleam is delayed, and every quiet star enters awareness as a message from elsewhere. Arriving late across the cold and measureless dark, beyond the single points of light that appear scattered across the night, stars gather into larger structures that give the universe much of its visible form. They are not placed evenly through space like grains across a flat surface. They belong to galaxies, to clusters, to associations, to pairs and families, and to long histories of motion shaped by gravity. From a greater distance, the sky changes from isolated lights into patterns of population. The Milky Way, which appears from Earth as a pale band across darkness, is not a cloud in the atmosphere or a decorative streak. It is the combined glow of vast numbers of stars spread through the disk of our galaxy, seen from within. That simple band is the visual sign that Earth lies inside a stellar system so large that the eye cannot separate most of its members. The stars of the galaxy occupy a broad, rotating structure with spiral arms, dense central regions, dark dust lanes, and outer zones where the density of stars gradually thins. To look into the Milky Way is therefore to look sideways through a crowded stellar environment. To look away from it is to peer towards sparser directions where fewer stars lie along the line of sight. The night sky changes with direction because the galaxy has shape. That shape is not immediately obvious to naked vision, yet it governs the distribution of visible starlight. The stars of the Milky Way are not random ornaments. They are members of a gravitational city with neighborhoods of different ages, masses, and histories. Within that city, many stars are born together. Giant clouds of gas and dust collapse into clusters and loose groupings, producing families of stars that share origin even if they later drift apart. Some open clusters remain recognizable for long spans, their stars moving together through the galaxy like companions with a common past. Others disperse gradually, their members mixing into the larger stellar population until the shared origin becomes difficult to trace. In the galactic halo and outer regions, globular clusters orbit as dense and ancient swarms containing some of the oldest known stars. These compact systems hold hundreds of thousands of stars in relatively small volumes, creating crowded environments unlike the more spacious neighborhood around the Sun. In such places, the sky from any orbiting world would not resemble the dark, spacious night known on Earth. It could be bright with nearby suns packed much closer together, their light altering darkness itself. The human image of a star as a solitary beacon in open night is therefore only one local version of stellar reality. Elsewhere, stars may belong to tight assemblies where closeness and crowding define the sky. Even in the local region, many stars do not live alone. A large fraction are members of multiple systems, bound to one another by gravity in pairs or larger groups. Two stars may orbit a common center, trading places in a long and graceful movement invisible to casual sight. Three or more may form more intricate arrangements, some stable across immense spans and others more delicately balanced. A point of light that appears singular from Earth may therefore hide a companion too dim or too close to separate without instruments. In some systems, the stars lie far apart and influence one another gently. In others, they are so close that their outer layers interact, shaping one another's development in profound ways. This means that solitude is not the default condition for every star. Many evolve under the steady influence of a neighbor. Gravity links them from birth onward, and their lives unfold not in isolation but in relationship. The nearest stellar system to the Sun itself is not a single star, but a multiple system. This is a reminder that the galaxy is full of complexity hidden behind apparent simplicity. A lone point of light can conceal an entire arrangement. From the scale of galaxies, another unsettling truth appears. Stars can survive changes that destroy the larger structures around them. Galaxies collide, merge, distort, and exchange material across billions of years. Their shapes are not permanent. Spiral systems can be stretched by tides, small galaxies can be stripped apart, and stars can be thrown into long new paths through violent gravitational encounters. A star born in one galactic environment may later find itself in another. Some are even ejected so forcefully that they leave their galaxies behind and drift through intergalactic space. These solitary travelers move through vast darkness far from any galactic home, carrying with them the history of forces that cast them out. Such stars reveal that galaxies, though enormous, are not unchanging containers. They are dynamic systems full of rearrangement. The stars inside them are at once residents and survivors. On the larger scales, then, the stellar world is structured but never fixed. Galaxies themselves gather in larger groups and clusters, separated by expanses so huge that even complete stellar systems seem like scattered dust. Within those galaxies, stars follow motions set by gravitational fields that change over time. The Sun, too, moves through the Milky Way, orbiting the galactic center over hundreds of millions of years. Its neighboring stars are not permanent companions, Some drift away while others draw nearer, altering the local stellar environment across deep time. The familiar constellations seen from Earth depend on this temporary arrangement. They feel ancient because human history is short, but they are only brief geometric patterns formed by stars at different distances moving along different paths. The eye turns them into figures and names, yet the galaxy does not preserve those designs. It allows them only for a while. This means the human map of the sky is local, cultural, and temporary, laid over a stellar distribution that has far deeper structure than myth can hold. From this regional view, stars become less like isolated lights and more like members of an immense living arrangement governed by gravity, motion, birth, dispersal, crowding, and escape. They fill galaxies without ever making them still. They gather, separate, orbit, and migrate through a universe where even the grandest structures remain in motion. The calm of the night therefore hides another secret. Behind every apparently quiet star lies a place in a larger system, and behind that system lies a longer history of gathering and change. The sky is not merely full of stars. It is full of stellar societies, hidden companions, ancient swarms, wandering exiles, and shifting neighborhoods, all moving within vast gravitational structures that no glance can reveal at once. Among the many stars spread through the galaxy, a small number grow to such extraordinary size that ordinary comparisons begin to fail. These are the giant supergiants and hypergiants, swollen stars whose outer layers expand so far from their centers that they seem less like compact suns and more like vast, unstable atmospheres loosely held together by gravity. Their existence reveals one of the first truly disturbing truths about stellar scale. A star does not need to resemble the Sun in proportion, density, or restraint. It can become so large that if placed where the Sun now stands, its outer layers would extend far beyond the inner planets, and in some cases deep into the outer solar system. The mind hears such measurements, but the feeling of scale remains difficult to anchor. Earth, which seems broad and complete in human life, would vanish without trace inside such a star. Even the orbit of Earth would not survive as a separate path. It would be enclosed within the star itself, immersed not in a hard surface but in an immense envelope of hot gas so extended and diffuse that the boundary between star and surrounding space becomes less distinct than expected. These larger stars do not possess a solid edge. Their outer regions thin gradually outward, and their atmospheres can be so inflated that the star resembles a slowly breathing sphere of light and matter, always losing material, always changing. What appears at a distance as a single stable star is, at closer scale, a tremendous and restless volume. Such enormous stars are rare because size at this level comes with instability. The same mass that allows a star to shine powerfully also creates severe internal pressure, intense radiation, and short lifetimes compared with quieter stars like the Sun. A star of extreme size lives quickly. It burns its nuclear fuel at a fierce rate, and the outward force of radiation presses so strongly through its outer layers that the star struggles to hold itself together. Its atmosphere may pulse, shift, and shed matter into surrounding space. Vast clouds of gas drift away from it, carrying material outward in slow waves or stronger winds. This means that the larger stars are not only huge, they are often in the process of unmaking themselves. Their scale is bound to fragility. A smaller star may remain comparatively stable for billions of years, but a hypergiant exists in a narrower and more dangerous balance. It has too much power moving through too much swollen material. The result is a body that seems magnificent from afar and precarious in physical reality. The unsettling nature of these stars lies partly in how they overturn familiar intuition. Human thought often treats size as a sign of durability, yet the stellar world does not follow that simple rule. The most enormous stars are often among the least secure. Their very size is evidence that they have reached a stage where their outer regions expand and loosen. Gravity grows weaker with distance from the centre, and the thin outer atmosphere can become easier to disturb, easier to lift, and easier to cast away. In some red supergiants and hypergiants, enormous convection cells rise and sink through the outer layers. These are not small currents like weather on a planet. They are colossal circulations, each spanning vast fractions of the star's visible surface. The star becomes a place of slow and gigantic motion, where the boiling of hot gas happens on scales that exceed entire planetary systems. The surface no longer behaves like a simple glowing shell. It flickers, swells, and shifts. Brightness changes. Shape becomes imperfect. The star departs from the ideal image of a round and fixed sun. Some of the largest known stars are so extended that they challenge precise measurement. Their boundaries are difficult to define because their atmospheres are diffuse, and because different wavelengths of light reveal different depths within the outer layers. Even the act of asking how large such a star is becomes more complicated than it first appears. There is no single hard shell from which to measure a clean radius. Instead, astronomers estimate where the visible atmosphere effectively ends, knowing that the answer carries uncertainty. This is another quiet source of unease. The largest stars are not merely big objects, they are giant zones of glowing gas with edges that blur into surrounding space. Their dimensions can be described, but not with the certainty one would use for a planet, a rock, or a machine. Their enormousness is real, yet their form remains partly unresolved, as though the star itself resists being neatly contained in definition. The red supergiants in particular display a slower and more sombre grandeur. Their colour reflects cooler outer layers, not weakness, but expansion. As the star's atmosphere swells outward, its surface temperature can fall even while the total size becomes immense. The result is a deep reddish glow spread across an enormous sphere. These stars do not blaze with the sharp blue intensity of hotter, massive stars. They radiate with a broader and softer appearance that can seem almost calm. Yet beneath that appearance lies a late and unstable stage of stellar life. The calm colour hides an approach towards structural failure. The star has already changed profoundly from its earlier state. It has exhausted simpler fuel in its core and now exists in a more complicated internal arrangement, with different layers burning different elements in shells around the centre. The outer immensity is therefore the visible sign of inner strain. Some giant stars also surround themselves with shells and clouds of material they have already lost. This expelled matter drifts outward and forms dusty or gaseous regions that can later become part of the wider interstellar medium. In this sense, the larger stars are not enclosed beings but leaking ones. They give part of themselves back to space long before their final destruction. Their winds enrich surrounding regions with heavier elements and prepare material that future stars and planets may one day inherit. Even here, however, the process remains destructive for the star itself. It is not growing into permanence. It is passing through a brief and unstable enlargement that cannot last. The immense star is already on the way toward ending, though that ending may still lie beyond direct sight. From a distance, these giant stars can seem like the ultimate form of stellar power, and in one sense they are. They display scale on a level that humbles every planetary frame of reference. Yet their deeper secret is not simply that they are large. It is that nature permits bodies of such terrifying extent to exist only in unstable compromise. They are inflated, temporary, difficult to define, and often already shedding themselves into space. Their beauty is inseparable from imbalance. Their grandeur is inseparable from nearing collapse. The largest stars, therefore, do not stand as monuments of permanence, but as luminous warnings written across the galaxy, showing that even the most colossal suns can become swollen, fragile, and short-lived when power grows too great for structure to bear. If the largest stars reveal the terrifying reach of stellar size, the most luminous stars reveal the equal danger of stellar power. Brightness in the stellar world is not only a visual quality, it is a physical statement about how much energy a star releases every second into the surrounding dark. Some stars radiate with such intensity that the outward flood of light and particles begins to reshape the star itself. These are not calm suns resting in stable equilibrium for long ages. They are fierce engines that consume their reserves rapidly, illuminate entire surrounding nebulae, and drive violent winds from their outer layers. Their brilliance is a warning sign. In the universe of stars, extreme brightness often means extreme instability, because the same energy that makes a star visible across great distances can also press outward against its own matter with relentless force. A massive star begins this life already burdened by excess. Its great mass crushes the core so strongly that temperatures and pressures rise to tremendous levels, allowing nuclear fusion to proceed at a much faster pace than in a smaller star. This increased rate does not bring patience or long endurance. It brings wasteful intensity. The star burns hotter, shines bluer, and races through stages of life that quieter stars cross only over billions of years. A giant blue star may live only a few million years before reaching crisis, while a more modest star can remain stable for spans so long that entire branches of planetary and biological history fit comfortably within them. The difference is one of scale, but also of temperament. Nature gives the massive star more fuel, yet it also compels that star to spend its fuel extravagantly. Great brilliance is bought with short time. This rapid consumption turns the most luminous stars into unstable presences in their galaxies. Radiation pressure rises through the interior and presses outward on the outer layers. Light, in this context, is not merely illumination. It carries momentum and can push matter. In ordinary stars, that outward push remains part of a long balance with gravity. In the brightest and most massive stars, however, the outward force becomes so severe that the outer atmosphere may begin to lift and flow away. Powerful stellar winds strip gas from the surface and send it outward into surrounding space. The star does not simply shine, it erodes. Its own light helps drive the loss of its own material. This is one of the strange and unsettling truths of extreme stars. Their brilliance is partly self-destructive. They can become so luminous that they struggle to remain intact under the force of their own radiation. Some of these stars pass through especially unstable phases in which their brightness and mass loss become even more dramatic. Luminous blue variables offer one of the clearest examples. These are massive stars in rare, turbulent states where the balance between gravity and outward pressure becomes delicate enough to produce eruptions, shifting temperatures, and major changes in the surrounding gas. The star may brighten, dim, or cast off enormous quantities of matter in episodes that alter both its appearance and its future. The process is not fully simple or uniform, and not every phase is understood in exact detail. But observations show that these stars can surround themselves with nebulae made from matter they once carried as part of their own bodies. A star in such a state is no longer merely living. It is shedding history into space. Around it forms a visible record of instability, a glowing archive of earlier violence. The fear these stars inspire does not come only from their energy, but from the scale of their indifference. Their radiation can dominate local regions of a galaxy, ionizing nearby gas, reshaping clouds, and influencing later star formation. Their ultraviolet light is intense enough to alter surrounding environments far beyond the star's visible disk. Their winds sweep across neighbouring space with enormous force. Yet for all this apparent supremacy, they remain temporary. The brighter and heavier the star, the faster it moves toward breakdown. There is no comfort in their magnificence because their magnificence is precisely what makes them unsustainable. They exist in a narrow and dangerous condition where power is both the mark of success and the cause of downfall. This relationship between mass, brightness, and brevity overturns a common instinct about greatness. It suggests that in the stellar world, excess does not create permanence, it shortens it. A very luminous star can outshine millions of quieter stars when measured by energy output, yet it cannot outlast them. It burns through possibility at such speed that its later stages arrive almost immediately on cosmic scales. The star becomes a brief blaze in galactic history. It is remembered not for endurance, but for impact. Its strong winds, intense light, and eventual death scatter influence through the surrounding medium, enriching the galaxy and altering the conditions from which later stars and planets may emerge. The most violent stars therefore help build future worlds, but they do so by destroying themselves at remarkable speed. Even before the final collapse, the star's surface and atmosphere may become increasingly disturbed. Layers swell, contract, or shift. The outer envelope can grow unstable under the competing effects of radiation, rotation, and internal structure. In some cases, the star becomes partially obscured by the very material it has expelled. Dust and gas gather nearby, illuminated by the star that cast them off. What is seen from a great distance as a brilliant beacon may therefore be a body already surrounded by the evidence of its own unravelling. It shines through the remains of matter it no longer holds. The most luminous stars are therefore not simply bright objects. They are demonstrations of what happens when a star approaches the limits of how much energy matter can release while still remaining bound to itself. They reveal that a star may become so radiant that its own light begins to tear at its structure, so powerful that its lifespan shrinks into a brief and volatile chapter. Their beauty is severe, blue, and magnificent, but it is never gentle. Behind their brilliance stands a harsher law. In the universe, the stars that shine most fiercely often live on the edge of ruin, and their light, however beautiful from afar, is the visible sign of a life being spent at a rate too great to last. Not all stars reveal their instability through sheer size or blinding brightness alone. Some show it through distortion, through shape altered by speed, through matter peeling away into surrounding space, and through shells of gas that hang around them like visible records of strain. The familiar image of a star is simple and nearly geometric, a round, glowing sphere suspended in darkness, balanced and complete. Yet this image is only partly true. Real stars can be stretched, flattened, wrapped in disks, and surrounded by expanding clouds that tell of violent loss. Their forms are shaped not only by mass and heat, but also by motion. Rotation, in particular, changes a star in ways that are both subtle from a distance and profound in physical reality. A rapidly spinning star does not remain perfectly round. The centrifugal effect, which is the tendency of rotating matter to move outward most strongly at the equator, causes the star to bulge around its middle and flatten toward its poles. The result is an oblate form, wider across the equator than from top to bottom. This is not a minor cosmetic difference. In extreme cases, the distortion becomes dramatic enough to change temperature across the star itself. The poles, pressed inward more tightly by gravity, can become hotter and brighter, while the equatorial regions, lifted farther from the centre, become cooler. The star then ceases to be even in its own surface conditions. It is not simply a globe of light. It is a rotating structure whose shape and temperature vary with latitude. This kind of distortion carries a quiet menace because it reveals how close some stars come to structural limit. Rotation stores energy. If the star spins too quickly, the outer material at the equator approaches the point where gravity can barely hold it. Matter then becomes easier to shed, and the star may cast gas outward into a surrounding disk. Seen from afar, such a star may look ordinary, but instruments reveal the presence of material orbiting around it, formed from gas that once belonged to the star's own outer layers. The star becomes a source of its own environment, building a ring or disk from matter thrown off by motion and heat. This surrounding gas may glow under the star's radiation, creating a more complex and less stable picture than the simple solitary star of imagination. The danger is not explosive in every moment, but continuous and physical. The star is spinning under such stress that its own form becomes difficult to maintain. Rotation also affects the star's interior life. Fast spin can mix layers that might otherwise remain more separate. Material from different depths may circulate more efficiently, altering how fuel is used and how the star evolves. This means that motion at the surface is not a surface matter only. The entire stellar body responds. The star lives differently because it rotates differently. The instability is written not only in its outline but in its internal timing. Even here, the stars resist simple categories. A star is not merely hot gas held by gravity. It is a dynamic body whose whole history can be redirected by speed. Around some stars, the evidence of loss accumulates in striking external shells. These shells may form through steady winds, repeated eruptions, or brief phases of instability when the outer layers swell and become easier to expel. Gas drifts outward and collects in arcs, rings, or diffuse expanding bubbles. Under the star's light, these structures may glow softly, revealing past episodes of shedding. In some cases there are several shells, one outside another, as though the star has repeatedly cast parts of itself into space in separate ages of unrest. Each layer marks a former disturbance. Each ring is a memory preserved in gas. Such stars appear clothed in their own history, surrounded by matter that no longer belongs to the central body, yet still remains tied to its life story. The star and its surroundings cannot be cleanly separated. The star changes by giving itself away. Some of the most striking examples of stellar mass loss occur in rare, massive stars with exceptionally strong winds. Wolf-Rayet stars belong to this category. These are hot, evolved stars that shed material at enormous rates, so forcefully that their outer layers are stripped back and deeper regions become exposed. Their spectra show the marks of this fierce outflow, and their surroundings may contain bubbles or shells carved by winds moving through nearby gas. A Wolf-Rayet star is not quiet or restrained. It is a body in the process of being uncovered by its own violence, revealing inner chemical layers that more stable stars keep hidden. Observations indicate that such stars represent advanced and dangerous phases of massive stellar evolution, and it remains uncertain in some cases exactly how prior binary interaction or earlier mass loss contributes to the path each one follows. What is clear is that these stars do not preserve themselves gently. They are being transformed by escape. Even more broadly, the idea of a star as a sharply bounded object begins to weaken in the presence of these shells, disks, and winds. A star can influence space far beyond its visible surface. It can fill nearby regions with outflowing gas, dust, radiation, and magnetic structure. It may appear centered within a local nebula that it partly created, or obscured by material it previously released. The visible stellar disk then becomes only the innermost part of a larger active system. This is one of the more unsettling lessons of close attention. Stars are not always compact lights against emptiness. Some are surrounded by evidence that they are unstable, leaky, and unfinished, forever exchanging material with the darkness around them. Through distortion and shedding, stars reveal a form of vulnerability different from collapse or explosion. It is slower, more physical, and in some ways more intimate. The star does not fail all at once. It strains, spins, loosens, and lets go. It flattens under its own speed. It drives gas away in winds. It wraps itself in rings and shells that testify to past unrest. What appears from a distance as a calm point of light may therefore be a body under continuous tension, reshaped by motion and marked by loss. In that sense, some of the stars are most frightening not when they flare or die, but when they quietly reveal that even their very shape is only a temporary compromise between gravity, pressure, and the relentless pull of change. Beneath the visible surfaces of stars, beneath their colour, their size, and their drifting shells of gas, there exists a quieter and more fundamental reality. Every star is governed by a balance so exact that its continued existence depends on it at every moment. Gravity pulls all of the star's mass inward without pause, always trying to compress the star into a smaller and denser state. Opposing that inward pull is the pressure created by the heat and energy released deep inside the star through nuclear fusion. A star survives only because these two forces remain in tension. It is not solid peace, but constant resistance. The star exists as a long negotiation between collapse and expansion, between inward weight and outward force. If gravity were left alone, the star would contract rapidly. If the outward pressure became too strong, the outer layers would expand. Stability is never an absence of conflict. It is the temporary success of balance. This balance begins in the birth of a star and defines everything that follows. A cloud of gas and dust collapses under its own gravity, and as the material falls inward, the center grows hotter and denser. Compression raises temperature. Temperature allows collisions between particles to become more energetic. Eventually, conditions in the core become severe enough for hydrogen nuclei to fuse and form helium. That process releases energy, and that energy pushes outward. The star then enters its long, stable phase, not because gravity has been defeated, but because gravity has been met by an equal answer from within. The energy generated in the core does not rush instantly to the surface. It moves outward slowly through dense internal layers, passing its influence through the body of the star and sustaining pressure against collapse. The star shines because of this energy, but its light is only the outer sign of a deeper struggle happening in the center. One of the quiet terrors of stellar existence lies in how absolute this dependence is. A star is not a permanent object that happens to glow. It is a process that must continue. Its shape, brightness, and survival all rely on energy being produced in the core and carried outward through the surrounding layers. If that process changes, the entire star must respond. The familiar image of a stable sun therefore hides a much less comforting truth. Stability is conditional. It depends on fuel, temperature, density, and the ability of the core to keep pressure flowing outward. The star looks calm only because the balance is successful for a time. Its apparent permanence is the outward face of continuous and exacting labour. Gravity in a star is immense. Every layer presses downward on the layers below, and the deeper one goes, the greater the pressure becomes. The core exists under conditions of such compression that matter behaves in ways far removed from ordinary earthly experience. Yet even this crushing inward force is not enough to destroy the star, as long as energy from fusion continues to resist it. In this sense, gravity is both creator and executioner. It creates the conditions needed for fusion by compressing the core to extraordinary heat and density. but it also waits for the moment when fusion can no longer answer it adequately. The entire life of a star takes place inside that paradox. Gravity makes the star possible, and gravity ensures that the star can never remain unchanged forever. This balance is not the same in every kind of star. In smaller stars, the tug of gravity is less severe and fuel is consumed more slowly, allowing very long stable lifetimes. In more massive stars, stronger gravity compresses the core more intensely, which drives faster fusion and far greater energy output. But the same faster burning that produces brilliance also shortens stability. The balance remains present, yet it becomes harder to sustain for long. More mass creates more pressure, but it also creates greater demand. The star must burn harder simply to remain itself. In this way, a star's mass determines not only how bright it shines, but how difficult its inner balance becomes to maintain across time. The internal structure that supports this balance is layered and dynamic. Energy created in the core moves outward by radiation in some regions and by convection in others, depending on temperature, density, and opacity. Convection is the movement of hot material upward and cooler material downward, a slow churning that helps carry energy through certain stellar layers. Radiation is the transfer of energy through repeated absorption and re-emission by particles packed within the star. These are not minor processes. They determine how efficiently the star transports the energy it must move outward in order to remain stable. If that transport changes, the outer layers adjust. The star may swell, contract, or alter its surface conditions. What is seen at the surface therefore depends on invisible decisions being made in the deep interior by matter under extreme pressure. Even the sun, often treated as a symbol of steadiness, lives on this knife edge. Its long stability reflects not immortality, but successful balance across billions of years. The sun remains what it is because its core continues to fuse hydrogen and maintain outward pressure. Its light falls gently on Earth, and that gentleness can mislead. It suggests ease, but the sun's continued form depends on a core where matter is compressed and heated to extraordinary conditions. Beneath the calm radiance lies constant violence controlled by balance. Every second, enormous numbers of nuclear reactions occur in the center, and every second that energy prevents inward collapse. The sun shines because it continually resists its own weight. A star, then, is not a simple object resting in space. It is a body perpetually holding itself up against gravity by means of energy released in its deepest region. Remove that energy, and gravity wins. Increase the demand too greatly, and the fuel is spent quickly. Disturb the flow, and the structure changes. The terror hidden inside every star is not merely that it can die, but that its very life depends on a fragile and exact contest that never ends while the star endures. The glowing sphere seen from afar is therefore not a static lamp in darkness. It is a maintained equilibrium, a controlled defiance of collapse, and a reminder that even the most constant stars shine only because, deep within, they are forever resisting the force that would otherwise destroy them. Inside the balance that keeps a star alive, the decisive process is fusion, the joining of lighter atomic nuclei into heavier ones under conditions of extreme temperature and pressure. This process is the hidden economy of a star. It determines how energy is made, how long stability can last, and how the internal structure changes with time. At the beginning of a star's long life, hydrogen serves as the primary fuel. In the core, immense heat allows hydrogen nuclei to overcome their natural electrical repulsion and combine through a chain of reactions that ultimately form helium. A small amount of mass is lost in the process, and that lost mass appears as energy. This energy is what pushes outward against gravity, in that sense. The star lives by converting part of its own matter into pressure and light. The glow seen from a great distance is the result of matter being slowly spent in the center. Even in the most tranquil star, the core is a place where stability is purchased by constant change. Hydrogen fusion can sustain a star for a very long time, but not forever. The supply in the core is finite, and as helium accumulates, the composition of the center changes. Helium does not behave like hydrogen. It requires greater temperature and stronger compression before it can begin to fuse. For a time, once core hydrogen is exhausted, gravity gains an advantage and the central region contracts. This contraction raises temperature further. In stars like the Sun, the outer layers respond by swelling outward, and the star enters a new phase. In more massive stars, the process continues through additional stages as the core begins to fuse successively heavier elements. Helium can form carbon and oxygen. In still more extreme cores, carbon, neon, oxygen, and silicon may also undergo fusion in later phases. The star becomes chemically layered, with different burning shells surrounding the center like nested zones of activity. Each stage tends to be shorter than the one before it. The deeper the star moves into advanced burning, the faster it spends what remains. A star nearing the end does not slow down. It accelerates toward crisis. This sequence reveals one of the darkest truths about stellar life. A star does not possess unlimited options for survival. Fusion releases energy only up to a point. For lighter elements, fusion can provide support against gravity. For heavier ones, that support becomes harder to achieve. The crucial boundary arrives with iron. Iron marks a turning point in nuclear physics because fusing iron or breaking it apart does not release usable energy in the way earlier fusion stages do. Instead, it consumes energy. This means that when a massive star builds an iron-rich core, it has reached a fatal threshold. The central engine can no longer gain support by proceeding to heavier fusion in the same manner. The process that held gravity back through the star's life now fails at its deepest level. This is why iron is not merely another element in the sequence. It is the sign that the star has reached the limit of what ordinary fusion can do for it. The core may still be held up briefly under extreme conditions, but once it becomes dominated by iron and related nuclei, the outward support from new fusion no longer provides a path forward. Gravity, which has waited through every earlier stage, begins to win decisively. The star has spent the very process that made it a star. Everything before this point has been a long resistance sustained by energy from fusion. At iron, that resistance runs out in principle, not just in quantity. The rules change. The core has crossed into a state where the old solution no longer works. Even before the final collapse, the late stages of burning in a massive star grow increasingly strange and compressed in time. Hydrogen burning may last millions of years. Helium burning lasts less. Later stages can shrink drastically, with silicon burning proceeding on timescales tiny by comparison. The star's inner life becomes a hurried sequence of brief and unstable achievements, each one extracting a little more order before failure becomes unavoidable. Outwardly, the star may still appear enormous and bright. Inwardly, it is moving through a chain of ever more desperate conditions. The center becomes a place of immense density, layered chemistry, and dwindling options. The star is still shining, but its final defeat is already written in the composition of the core. In smaller stars, the story ends before iron is ever reached. Stars with lower mass do not achieve the extreme core temperatures needed for the advanced burning of heavy elements. Their fate is quieter, and their interiors never pass through the full sequence that massive stars endure. Yet even there, the principle remains the same. A star survives only while fusion can provide the pressure required to counter gravity. Once the relevant fuel is exhausted or the next stage cannot begin under available conditions, the balance shifts. The star must change because its core can no longer remain as it was. The terrible elegance of stellar evolution lies in this unavoidable progression. The same fusion that gives warmth, light, and stability also carries within it the seeds of ending. Every successful reaction alters the composition of the core. Every stage of burning solves one problem while creating the conditions for the next and harder one. The star survives by using fuel, and in using fuel it transforms itself step by step into a structure that can no longer be supported indefinitely. This is not an accident or a disturbance from outside. It is the natural consequence of the star's own inner success. From the outside, a star seems like a constant source of radiance. From the inside, it is a slow sequence of thresholds, each one more severe than the last. Hydrogen gives way to helium to heavier elements, and in the most massive stars the path leads at last to iron, where the long bargain between fusion and gravity reaches its end. What makes a star live is the same process that carries it toward the point where life as a star can no longer continue. The core does not merely power the star, it prepares its fate, element by element, in a silence so deep and hidden that the surface can still shine serenely, while the center moves toward the fatal moment when gravity will no longer be denied. When a star like the Sun nears the end of its long, stable life, the transformation is not immediate violence, but a slower unraveling shaped by the loss of balance in the core. Hydrogen fusion in the center cannot continue forever. As helium accumulates and usable hydrogen in the core is depleted, the central region contracts under gravity and grows hotter, while fusion shifts outward into a shell surrounding the core. This change in structure forces the outer layers to respond. They expand enormously, cool at the surface, and the star enters the red giant phase. From a distance, the red giant can appear majestic, larger and more luminous than before, glowing with a deeper orange or red tone. Yet this enlarged appearance is not a sign of renewed strength. It is evidence that the star has left behind the long, steady condition that defines most of its life. The star has become larger because its internal arrangement has changed, and because the energy produced in shell burning now pushes the outer layers outward. A once compact and familiar sun becomes swollen and altered, its outer atmosphere extended far into surrounding space. For a planetary system close to such a star, this is not a graceful aging, but a profound threat. Inner planets may be scorched, stripped, engulfed, or left sterile under the changing radiation and expanding stellar envelope. The star that once supports life can become the agent that ends it. In stars of modest mass, this phase does not continue into the full sequence of advanced burning found in massive stars. The core can become hot enough for helium fusion, producing carbon and oxygen, but it cannot generally move far beyond that. This limitation defines the quieter ending. The star does not build an iron core. It does not collapse in a core collapse supernova. Instead, it reaches a point where the outer layers become increasingly unstable and only loosely bound. Pulsations and stellar winds strengthen. Gas drifts away from the star in expanding shells. Over time, the outer envelope is shed, leaving the hot core exposed. The surrounding material, lit by ultraviolet radiation from that core, can glow as a planetary nebula. The name is historical and misleading, since it has nothing to do with planets in origin. It is really a brief luminous cloud, a final visible display produced when a dying ordinary star illuminates the gas it has cast off. The shapes of these nebulae can be round, elliptical, or more complex, influenced by magnetic fields, companion stars, and the geometry of mass loss. What remains at the centre is no longer a normal star, but a white dwarf. A white dwarf is one of the strangest quiet endings in the universe. It contains a mass comparable to that of the Sun compressed into a volume closer to that of Earth. There is no active core fusion sustaining it in the old way. Its support comes instead from electron degeneracy pressure, a quantum mechanical effect that arises when matter is compressed so strongly that electrons resist being forced into the same states. This pressure does not depend on temperature in the ordinary way, which means the white dwarf can remain structurally supported without continuing the nuclear burning that once defined the star. In this remnant, gravity has pushed matter to an extraordinary density, but collapse stops short of the more catastrophic states reached by massive stellar cores. The white dwarf is therefore a dead core that still glows, radiating leftover heat into space. It shines not because it is making large new energy, but because it is cooling from the immense thermal history of its former life. This gives the white dwarf a haunting quality. It is a stellar corpse that remains visible for immense spans. At first, it may be hot and bright enough to stand out clearly, but over billions of years it slowly fades. There is no rescue hidden in that fading. The white dwarf has no new fuel source capable of restoring its earlier life as a stable, fusion-powered star. It simply cools. The universe is not yet old enough for any white dwarf to have completed that cooling all the way to a black dwarf, a remnant so cold that it emits essentially no visible light. Black dwarfs therefore remain theoretical future objects, expected from known physics, but not yet present in the observable universe because time itself has not advanced far enough. This fact introduces another layer of unease. The endings of ordinary stars extend beyond the current age of the cosmos. The future contains classes of dead stars that no observer has yet seen because the universe is still too young for their arrival. The death of a modest star is quieter than a supernova, but quiet does not mean gentle. For any nearby worlds, the red giant phase can erase familiar conditions completely. The later shedding of the outer envelope changes the radiation environment again, and leaves behind a white dwarf whose light is faint compared with the living star that came before. A planetary system that once circles a warm main sequence, star may end as a field of scorched remnants, altered orbits, frozen outer worlds, and a small dense ember at the centre. The transformation is a complete rewriting of the local system. What seemed stable for billions of years turns out to be temporary on stellar timescales. There is also something deeply unsettling in the nature of the white dwarf itself. It is matter preserved in a state that ordinary earthly experience never suggests. A spoonful of such material, if it could exist under Earth conditions without exploding into expansion, would weigh enormously. The remnant remains supported not by heat-driven expansion, but by the rules of quantum physics acting under great compression. In life, the star resists gravity through fusion. In death, it resists gravity through degeneracy pressure. The method changes completely, but the contest continues in altered form. The white dwarf is therefore not an ending in the sense of disappearance. It is an ending that leaves behind an object both stable and profoundly unnatural to human intuition. Ordinary stars do not conclude with the spectacle of total destruction. They conclude with expansion, shedding, exposure, compression, and cooling. Their final gift to space is the release of outer layers enriched by earlier burning, while their final core becomes a dense remnant that fades only across unimaginable spans. The terror in this ending is not sudden catastrophe, but inevitability. A calm and familiar star can spend billions of years appearing dependable, and then, by the ordinary unfolding of its own inner physics, become a giant, cast off its atmosphere, and leave behind a compact white remnant drifting through the long future. In this way, Even the gentler deaths of stars reveal the same truth found elsewhere in stellar life. Stability is temporary, and what looks eternal from within one brief lifetime is often only the middle of a process that ends in loss, exposure, and slow, cold fading. For massive stars, the ending is not a slow fading into a compact ember, but a violent collapse that can briefly outshine entire galaxies. These stars spend their lives building toward a crisis hidden deep in the core. After progressing through successive stages of fusion, they reach the fatal point where iron accumulates in the center, and no further ordinary fusion can produce the outward energy needed to resist gravity. At that moment, the long tension that holds the star up begins to fail catastrophically. The core loses support and collapses inward with astonishing speed. Electrons are forced into protons, forming neutrons and releasing vast numbers of neutrinos, nearly massless particles that escape almost unhindered through surrounding matter. The collapse drives densities upward so rapidly that the inner core becomes incomprehensibly compact. What has been a star for millions of years now enters a terminal event that unfolds in seconds. Gravity, which has waited through every stage of the star's bright life, suddenly overwhelms the old balance and forces matter inward in one of the most dramatic transformations known in nature. The collapse does not end quietly at the center. In many such stars, the infalling material crashes against the newly compressed core and generates a powerful shock. The details of how this shock is revived and carried outward are complex, and observations together with theory indicate that neutrinos play a crucial role in helping transfer energy to the stalled shock so that the outer regions can be driven off in a supernova explosion. It remains an active area of research exactly how the full mechanism unfolds in every case. But what is certain is that the outer layers of the star can be blasted into space with enormous force. The explosion tears the star apart, drives shock waves into surrounding gas, and sends newly forged elements outward into the interstellar medium. For a brief time, the dying star can rival the light of all the stars in its home galaxy combined. The event is so bright because an immense store of gravitational collapse energy is suddenly converted into motion, radiation, and heat. A star that spends millions of years gathering fuel and building layered complexity releases its ending in a short, devastating burst. This form of death is called a core collapse supernova, and it is both a destruction and a redistribution. The star's previous structure is erased. Its outer layers, once held in place by gravity and pressure, are thrown outward into surrounding space. The local environment is changed forever. Nearby gas can be compressed by the blast wave, magnetic fields can be reshaped, and the expanding remnant can glow for thousands of years as shock-heated material moves through the region. In this sense, the supernova is not just the death of one star. It is an event that rewrites part of a galaxy around it. The star ends by striking its surroundings with light, motion, and enriched matter. The violence is not decorative, it is formative. Without these explosions, the galaxy would hold fewer heavy elements and fewer triggers for future rounds of star formation. Yet even within this broad category, stellar death does not always follow a single simple script. Some massive stars appear to pass through unusual eruptive stages before their final destruction, and a rare class of events shows that a star can suffer major outbursts, survive temporarily, and then later explode more completely. In especially massive stars, theory predicts something called pulsational pair instability. Under extreme temperatures, energy in the core can be converted into pairs of particles and antiparticles, reducing the radiation pressure that helps support the star. The core then contracts, heats further, and may trigger explosive burning that ejects large amounts of mass without fully destroying the star at first. The process can repeat in pulses, the star becomes unstable in episodes, casting off shells of gas and temporarily recovering before the final collapse or disruption. Observations of certain bright transients indicate that some stars do undergo repeated violent outbursts before the end, though the exact classification of each event remains an area where evidence must be interpreted carefully. What emerges clearly is that some massive stars do not die in one clean moment. They struggle, erupt, and partially survive before surrendering. This possibility makes their final years especially unsettling. A star that has already become unstable may surround itself with dense shells of gas lost in earlier eruptions. When the ultimate supernova blast arrives, it can collide with that previously ejected material, producing extraordinary brightness as the shock plows through the dense environment. The final display then includes not only the collapse of the core, but the violent interaction between present explosion and past unrest. The star dies inside the remains of its own earlier instability. It is as though the star's history waits nearby to amplify the force of the end. There is also a profound asymmetry between appearance and reality in these last stages. From afar, a massive star may continue to shine with outward grandeur, even while its core races through short advanced burning phases and approaches failure. The surface can remain luminous and apparently complete while the central regions move toward irreversible collapse. A star may look magnificent in the sky, while its deepest layers are only days, hours, or seconds from destruction. This hidden timing is part of what makes massive stellar death so severe. The final disaster begins out of sight, in a core no telescope can directly observe. Only afterward does the star announce what has happened, and when it does, the announcement is an explosion visible across cosmic distance. The supernova is therefore more than a bright ending. It is the moment when a star's long internal history is converted into an outward catastrophe. The layered burning, the iron threshold, the gravitational defeat, the flood of neutrinos, the outward blast, and the dispersal of matter all converge in one event. Some stars die cleanly in this fashion, some may pulse and erupt before the end, but in each case, the deeper truth remains the same. Massive stars do not simply go dark, they collapse under their own weight, and in doing so unleash a force so great that the end of one star becomes a visible event for an entire galaxy. A final act in which the star destroys itself and changes the cosmos around it at the same time. What remains after a massive star collapses can be stranger than the star that came before. When the core of such a star is crushed during a supernova, the outward explosion may tear away the outer layers, but the center does not necessarily vanish. If the remaining core mass falls within a certain range, gravity compresses it so intensely that electrons and protons combine into neutrons, and the remnant becomes a neutron star. This object is small by stellar standards, often only about 20 kilometers across, yet it can contain more mass than the Sun. The result is matter packed to a density so extreme that ordinary comparison fails. A mountain of neutron star matter reduced to a spoonful would weigh billions of tons under Earth gravity. This is not simply compactness in the everyday sense. It is a condition in which matter has been pressed beyond familiar atomic structure into a state governed by the crushing dominance of gravity and the quantum rules that resist further collapse. The star that once spread across millions of kilometers may leave behind a remnant smaller than a city, yet denser than anything humans can directly experience. A neutron star is one of the clearest examples of nature taking a known substance and forcing it into an almost unrecognizable state. In an ordinary atom, most of the volume is empty space around a tiny nucleus. In a neutron star, that spacious structure is gone. Matter is compressed until atomic distinction largely disappears, and the core becomes a dense sea dominated by neutrons. The surface, insofar as a surface can be described for such an object, may consist of extraordinarily compressed nuclei and electrons arranged in forms unlike normal matter on Earth. Beneath that lies an interior where the exact state of matter remains an active area of scientific study. Observations indicate that neutron stars contain layers with different properties, and it remains uncertain in full detail how matter behaves at the deepest densities, including whether more exotic forms appear in the inner core. What is known is already unsettling enough. A star can die and leave behind an object whose matter is so compressed that the usual picture of atoms no longer applies. Even though a neutron star is tiny compared with an ordinary star, it is not weak. Its gravity at the surface is immense. A person standing there, if such a thing were possible, would be crushed instantly beyond recognition. Time and light behave differently in such a strong gravitational field, and escaping the surface requires enormous energy. Yet despite its small size, the neutron star can still make itself known across the galaxy. Some are born spinning rapidly, because the parent star's rotation is conserved as the collapsing core shrinks. Just as an ice skater spins faster by drawing in the arms, a stellar core rotating modestly before collapse can become a remnant rotating many times per second once compressed to a much smaller radius. This rapid spin, combined with strong magnetic fields, produces one of the most remarkable stellar remnants known, the pulsar. A pulsar is a rotating neutron star that emits beams of radiation from regions near its magnetic poles. These beams do not usually align with the rotation axis, so as the star spins, the beams sweep through space like the light from a lighthouse. If Earth lies in the path of that beam, instruments detect a regular pulse each time the rotation brings it into view. The pulses can be extraordinarily precise, so precise that some pulses rival or exceed the timing stability of the best clocks over long intervals. What appears as blinking is not a star turning on and off, but a beam crossing the line of sight again and again with exact repetition. This precision gives pulsars a special place in astronomy. They're not only exotic remnants, but natural clocks that can be used to test physical laws under extreme conditions. The existence of pulsars carries a special kind of terror because of the contrast between their size and their behavior. A body no larger than a city can spin hundreds of times each second. The surface speed near the equator becomes astonishing. The magnetic fields remain immense. The remnant of a dead star then sends regular flashes through the galaxy with such rhythm that early observers briefly wondered whether the signals might be artificial. That interpretation did not last, but the fact that nature itself could produce an object so compact, so fast, and so exact remains deeply striking. The pulsar is a dead core behaving with a level of precision that feels almost designed, though it arises entirely from the consequences of collapse, magnetism, and rotation. As pulsars age, they generally lose rotational energy and slow down gradually. Their pulses lengthen, their activity changes. Some may also be spun up again in binary systems if they gain matter from a companion star, becoming millisecond pulsars that rotate with breathtaking speed. These recycled pulsars show that even after stellar death, interaction with a companion can alter the remnant profoundly. A neutron star is not always a final silent cinder. It can remain dynamically engaged with its surroundings and continue to reveal itself through radiation, spin, and gravitational effects. The deeper significance of neutron stars and pulsars lies in what they show about the fate of matter under pressure. They mark the point where collapse does not yet become a black hole, but goes far beyond any ordinary star or planet. They are the surviving cores of stellar catastrophes, left behind when gravity defeats normal atomic structure, but is still held back by neutron degeneracy pressure and the strong nuclear force. A neutron star is therefore not simply a leftover fragment. It is a boundary object, perched between star and something even darker. In the life of a star, the neutron star is a frightening answer to the question of how far gravity can go without complete disappearance. In the life of the universe, the pulsar is one of the most precise and haunting reminders that stellar death does not always end in silence. Sometimes it leaves behind a remnant so dense that matter itself is transformed, and so rapidly spinning that a dead star keeps speaking across space in pulses of light and radio waves, marking time in the darkness with the steady rhythm of a collapse that never truly stops astonishing those who observe it. Among the remnants left behind by stellar collapse, magnetars stand as some of the most extreme objects known in the universe. They are a special kind of neutron star, born from the same general catastrophe that produces other collapsed stellar cores, yet marked by magnetic fields of almost unimaginable strength. A neutron star is already a place where matter is compressed beyond ordinary atomic form, where gravity holds more than a solar mass inside a body only about the size of a city. A magnetar takes that condensed remnant and adds a level of magnetic intensity so severe that the object becomes an extraordinary laboratory for physical processes that cannot be recreated on Earth. The field of a magnetar can be thousands of times stronger than that of an ordinary pulsar and vastly beyond anything produced in human technology. In such an environment, magnetism is not a minor property. It becomes one of the defining forces shaping the behavior of the star, its surface, and the space immediately around it. Magnetars likely arise when a collapsing stellar core forms under conditions that preserve or amplify magnetic structure during the violent compression of the supernova event. The exact details of how the strongest fields are generated remain an area of active study, but observations indicate that rapid rotation and internal fluid motion in the newborn neutron star may help build the immense magnetic strength. What results is not merely a dense remnant with a strong field, but an object whose magnetism can dominate its outer layers and drive violent activity long after the explosion that created it has faded. The magnetic field may become twisted, stressed, and unstable, storing energy that can later be released abruptly. In this way, the magnetar does not simply sit in the aftermath of collapse. It carries a continuing form of danger within itself, held in tension by its own field. The scale of that field is difficult to place into ordinary language without sounding exaggerated, yet the scientific reality is already severe enough. Magnetic forces near a magnetar can distort the behavior of matter and radiation in ways that have no parallel in everyday experience. At those strengths, the magnetic environment affects atoms, the motion of charged particles, and the structure of the space just above the surface. The crust of the magnetar, which is an ultra-dense solid layer overlying deeper interior matter, can come under enormous stress as the internal magnetic field shifts. When that stress grows too great, the crust may crack or rearrange abruptly. The result can be a sudden release of energy observed as a burst or flare of high-energy radiation. These events are among the most violent outbursts seen from stellar remnants. A magnetar that has been quiet can suddenly release in a fraction of a second an amount of energy greater than the sun emits over very long spans. This activity gives magnetars a disturbing character distinct from the rhythmic precision of pulsars. A pulsar often speaks with regularity, its beam returning again and again with dependable timing. A magnetar behaves more like a body under hidden internal stress. Quiet for a time and then abruptly explosive, it may emit repeated bursts, larger flares, and episodes of changing spin or brightness that reflect the restless nature of its magnetic structure. These are not random in the sense of having no cause, but they are the result of an internal system under extreme pressure, where the rearrangement of field lines or crustal fracture can release catastrophic energy on very short timescales. The star is dead in the old sense that fusion no longer powers it. yet it remains violently active because its magnetic field stores and releases energy in its own separate way. One of the most unsettling truths about magnetars is that they show how stellar death can create not only compact remnants, but ongoing engines of extreme physics. The star that once burned by fusion has already collapsed and exploded, yet what remains is not silence. It is an object whose field can be so strong that it shapes the vacuum and the motion of light itself in measurable ways. The radiation emerging from near a magnetar carries the marks of conditions so severe that theory and observation must work together carefully to interpret them. In some cases, bursts from magnetars have been detected across huge distances, briefly outshining many other sources in the high-energy sky. These flashes are reminders that even a remnant only a few kilometers wide can dominate observation for a moment when physical conditions become intense enough. There is also something profoundly disturbing in the imbalance between scale and effect. A magnetar is tiny compared with the star that produced it. It no longer occupies millions of kilometers or bathes nearby space with the broad, steady light of a living sun. Yet the compactness of the remnant allows extreme conditions to gather into a small volume. The energy is concentrated, the field is concentrated, the gravity is concentrated. The object becomes less impressive in size and more terrifying in intensity. This reversal is part of what makes magnetars feel so alien. They reveal that the universe does not always express power through vast extension. Sometimes it compresses power into a very small place and lets the consequences grow more severe because of that compression. Magnetars also matter because they expose the limits of what is known. Observations indicate much about their bursts, spin, and fields, but the exact state of matter inside them, the full geometry of their magnetic structure, and the detailed trigger of every major flare remain areas with important open questions. This uncertainty does not weaken their significance, it deepens it. They are objects where the laws of matter, gravity, and magnetism meet under conditions that push theory hard. To study them is to study a frontier, one that begins not in distant speculation but in real remnants observed across the galaxy and beyond. In the layered story of stellar secrets, magnetars occupy a place where death becomes harsher rather than quieter. They show what happens when collapse produces not only density and rotation, but magnetic force raised to a level that can fracture crust, release blinding radiation, and reshape the environment around a stellar corpse. The star is gone, yet its remnant remains capable of violence beyond ordinary imagining. In that sense, the magnetar is one of the purest expressions of the universe's hidden severity. It is a dead star whose field is so strong that it turns the aftermath of collapse into a continuing state of tension, a condensed fragment of stellar history still dangerous long after the original sun has ceased to be. In the regions near black holes, the ordinary idea of a star as a self-contained body becomes fragile. Gravity there is no longer simply the inward force that shapes a star from within. It becomes an external power so overwhelming that it can redirect, strip, accelerate, or destroy the star outright. A black hole does not need to touch a star in any ordinary sense to dominate its fate. If a star passes too close, the difference in gravitational pull between the side nearer the black hole and the side farther away can become extreme. This difference is called a tidal force, and in the most severe cases it stretches the star into a long stream of matter. The event is known as a tidal disruption. What had been a coherent star becomes elongated, torn apart, and converted into an expanding stream of gas. Part of that material escapes outward, part spirals inward to form a hot accretion flow around the black hole. As the gas falls deeper into the gravitational well, it heats intensely and can radiate invisible light, ultraviolet light, X-rays, and other wavelengths. For a time, the destruction of a single star may produce a flare bright enough to rival the glow of much of its host galaxy. The star disappears not in silence, but in a brilliant declaration of what gravity can do when it becomes the dominant force. This form of stellar death is especially unsettling because it strips away the idea that stars are secure in their own mass and power. A star can be enormous, hot, and long-lived, yet near a black hole those qualities may offer no protection. The black hole does not destroy the star by explosion from within or by opposing fusion. It destroys by differential gravity, by pulling unequally across the star's body until the star's own self-gravity can no longer hold it together. The violence is therefore geometric as much as energetic. The star is not merely crushed, it is pulled apart. Matter that once orbits quietly within a stellar structure is redistributed into arcs, streams, disks, and jets. The black hole turns a star into fuel and display at the same time. Astronomers identify tidal disruption events by observing sudden flares near galactic centers, followed by changes in brightness over months or years as the disrupted material continues to fall inward. These observations provide valuable evidence because black holes themselves emit no light directly. The destroyed star becomes the means by which the otherwise dark object announces its presence. In that sense, the flare is both an ending and a revelation. The black hole is made visible by what it consumes. The star, in dying, briefly illuminates the thing that destroys it. This gives the event a cruel symmetry. The victim becomes the source of the only visible trace. Not every star that approaches a black hole is torn apart. Some survive on extreme orbits, especially around supermassive black holes at galactic centers. In the Milky Way, stars have been observed moving rapidly around the central black hole called Sagittarius, a star. Their orbits provide some of the strongest evidence that a supermassive black hole occupies the galactic center. One of these stars passes within a surprisingly small distance on astronomical terms, moving at thousands of kilometers per second at closest approach. The star survives because it does not cross the threshold where tidal forces overwhelm its own gravity. Its motion becomes a kind of testimony, tracing the invisible mass around which it swings. These stars show that black holes do not always destroy what comes near. Sometimes they impose extreme order instead, binding stars into swift and deeply curved paths that reveal gravity in near its most severe form. There is another outcome as well. A star approaching a black hole under the right conditions can be accelerated and thrown outward at tremendous speed. These hypervelocity stars move fast enough to escape the galaxy entirely. Their origin may involve close encounters with the central black hole or with black hole binaries, where gravitational interactions convert orbital energy into outward flight. The result is a stellar exile, a star cast out of its home system and sent into intergalactic space. This is a different kind of destruction, not of the star's body but of its belonging. The star survives, yet it becomes a wanderer in the dark between galaxies, separated from the environment in which it formed. For any planets that might remain bound to such a star, the sky would be transformed beyond recognition. The familiar crowding of galactic starlight would fall away, replaced by vast solitude. These different outcomes reveal the range of black hole influence on stars. One star may be torn into a flare, another may survive on a close orbit that tests relativity, another may be slingshot outward and lost to the galaxy. In each case, the black hole acts not by surface contact or visible weapon, but by gravity so strong that it rewrites motion and structure at a fundamental level. The star remains subject not only to its own internal balance, but to the geometry of space-time around it. Near a black hole, the old security of stellar self-containment ends. a star becomes vulnerable to external gravity on a level far beyond ordinary galactic life. This is what makes black holes especially terrifying in the story of stars. They're not simply another stage of stellar evolution. They're regions where gravity can dominate so completely that a star's size, temperature, and long history may count for little. A star may orbit in their shadow, be hurled away by their pull, or be torn apart and turned into light by falling toward them. The black hole itself remains dark, but the effects on nearby stars can be violent, bright, and undeniable. Through those effects, the universe reveals one of its harshest truths. Even stars, which seem to stand for permanence and radiant power, can become fragile when they pass too near the deepest wells of gravity, where structure yields to tidal force and light itself emerges from destruction. When stars collide or merge, the event does more than destroy existing structures. It creates new signals, new elements, and new evidence about the deep workings of the universe. In ordinary thought, stars seem too far apart and too large to imagine as bodies that meet directly. But in close binary systems, gravity can bind two compact remnants into a long inward spiral. As they orbit one another, they lose energy through the emission of gravitational waves, which are ripples in space-time predicted by general relativity. These waves are not light. They are distortions in the structure of space and time themselves, spreading outward at the speed of light as the orbit tightens. For long periods, the loss is gradual, but as the objects draw closer, the process accelerates. The orbit shrinks, the speed rises, and the final moments become a rapid plunge toward contact. If the pair consists of neutron stars, the merger is one of the most extraordinary events known. Two stellar remnants, each already denser than any normal star, crash together in an outburst that releases both gravitational waves and electromagnetic radiation across multiple wavelengths. The event is violent enough to alter matter at the nuclear level and bright enough to be observed across immense cosmic distances. The detection of such a merger marked a turning point in astronomy because it allowed the same event to be observed through two different messengers. Gravitational wave detectors recorded the space-time signal, while telescopes observed light from the aftermath. This combination revealed that the collision of neutron stars is not only a dramatic end for the binary system, but also a source of heavy elements. In the extreme conditions of the merger, matter is compressed, heated, and thrown outward in such a way that rapid neutron capture can occur. This process, known as the R process, builds some of the heaviest elements in nature, including gold, platinum, and others too difficult to form in ordinary stellar interiors. The collision therefore becomes a forge unlike the long, steady burning inside a main sequence star. It is brief, explosive, and nuclear in a different register. Matter is assembled into rarer forms during the violence of impact, and those elements are then scattered into surrounding space where they may later become part of planets, rocks, and living worlds. This changes the meaning of beauty and wealth in a quiet but unsettling way. Precious metals on Earth are often valued for rarity and permanence, yet part of their origin lies in collisions so violent that space-time itself rings from the impact. A gold atom may owe its existence not to a gentle stellar glow, but to the wreck of two neutron stars locked together in a fatal orbit for millions or billions of years. The calm object held in a human hand can therefore trace its origin back to one of the harshest events in the cosmos. The universe hides this history well. Matter looks ordinary once it cools and gathers into planets, but its deeper ancestry may include catastrophic mergers far beyond any human scale. Not all stellar collisions involve neutron stars. White dwarfs in binary systems can also interact, transfer matter, and in some cases merge. Under the right conditions, a white dwarf gaining matter from a companion may approach a critical mass and ignite a thermonuclear runaway. This is the basis of a Type 1 supernova, one of the most important tools in cosmology. Because these explosions reach a fairly consistent peak brightness, they can be used as standard candles to estimate cosmic distance. By comparing how bright such an event appears from Earth to how bright it is known to be intrinsically, astronomers can infer its distance. These measurements played a central role in the discovery that the expansion of the universe is accelerating, a result linked to what is called dark energy. In this way, the death of a compact star becomes a measuring instrument for the larger scales in existence. A star does not simply explode. It becomes a marker by which the size and behavior of the universe can be traced. There is something deeply strange in this. The same stellar violence that destroys one system provides the information needed to understand reality on the grander scale. A supernova becomes a ruler. A merger becomes a signal in space-time. Catastrophe becomes method. The universe offers knowledge, but often only by way of destruction. The star must collapse, merge, ignite, or tear itself apart before it reveals the deeper conditions that govern everything else. These collisions and explosions also show that death in the stellar world is rarely a clean disappearance. The end of one form becomes the beginning of new chemistry, new structures, and new observations. A neutron star merger sends heavy elements outward. A Type 1. A supernova seeds surrounding space and helps map the cosmos. A violent event that lasts seconds, days, or months may leave traces that shape galaxies for ages. In this sense, the stars do not merely die, they convert collapse into consequence. The energy released at the end does not remain local. It travels outward as radiation, shock, and matter, altering what comes later. This is one of the most terrifying secrets hidden in the story of stars. The universe creates richness through violence. It does not reserve its most important acts for peace or stability. Some of the elements that make complex worlds possible are forged not in calm, long-lived suns, but in collisions where dense stellar remnants merge under the pull of gravity until their final impact sends ripples through space-time and debris across interstellar space. The cosmos is not only a place of light and motion, it is a place where endings can become factories, where destruction can become measurement, and where the crash of dead stars can shape the chemistry of life and the understanding of the universe at once. To study such events is to recognize that some of the deepest forms of creation do not arrive gently. They arrive through collision, signal, and fire, leaving behind both matter and meaning in the dark. The matter that makes bodies, oceans, rocks, and air does not begin on Earth, it begins in stars. This statement can sound poetic, but in scientific terms it is one of the most direct and unsettling truths in all of astronomy. The early universe contains mostly hydrogen and helium, with only very small amounts of lithium and almost none of the heavier elements required for planets, chemistry, and living systems. Those heavier elements must be made later, and stars are among the primary places where that making occurs. In their cores, stars fuse lighter nuclei into heavier ones, building elements such as carbon, oxygen, neon, magnesium, and silicon over time. More violent stellar deaths and mergers then scatter these elements outward, mixing them into interstellar clouds from which new stars, planets, and eventually biological systems can form. The human body is therefore not merely located beneath the stars, it is materially descended from them. The carbon in living cells, the oxygen in the atmosphere, the calcium in bones, and the iron in blood all trace their origins back to stellar processes that unfold across vast spans of time before Earth exists. This makes human existence part of a much older circulation of matter. A star forms, burns, changes its chemistry, and sheds material through winds or explosive death. That material drifts into the interstellar medium, where it may remain for long ages before becoming part of a new molecular cloud. Later, that cloud may collapse into a fresh generation of stars and planets. Some of the same atoms that once moved through the outer layers of a giant star may later become locked in rock, water, atmosphere, or living tissue on a planet orbiting a younger sun. The continuity is literal. Matter is reused. The universe does not discard the products of stellar life. It recycles them into new structures. What appears separate on the scale of one human life is linked over cosmic time by the long motion of elements from one system to the next. There is something profound and slightly terrifying in this continuity, because it removes any simple boundary between life and the violent history that precedes it. The materials of a peaceful living world do not arise from gentle origins alone. Iron owes its presence to stellar fusion and supernova history. Gold may trace its path back to neutron star mergers. Carbon, which forms the framework of organic chemistry, is built inside stars that live and die, according to the same physical laws that govern every other stellar object. Human softness, memory, thought, and breath all depend on atoms forged under conditions of extreme heat and pressure long before the planet exists to host them. This means that the body carries within it the record of ancient astrophysical violence. Life is not separate from cosmic severity. It is one of its later outcomes. The star therefore occupies a double role. It is both creator and destroyer. During life, it builds heavier elements through fusion. In death, it may scatter those elements back into space, often through strong winds, planetary nebulae, supernovae, or mergers. Without these cycles, the universe would remain chemically poor. There would be hydrogen and helium in abundance, but the rich periodic diversity required for rocky worlds and biological systems would be severely limited. Complexity depends on stellar generations. The first stars enrich the medium. Later stars form from enriched gas and create still more varied conditions. Planets condense from disks already containing the products of earlier stellar history. By the time a world like Earth forms, it already inherits a chemical legacy composed over billions of years. This also means that when a person looks at the stars, the relation is not merely observational, it is ancestral in material terms. The connection does not depend on metaphor. The body contains atoms that once belonged to older stars, and that later may return to wider cycles of matter again. The boundaries that feel absolute at human scale are not absolute in the long chemistry of the universe. A living being is a temporary arrangement of ancient particles. The stars make those particles available. Planets gather them. Biology organizes them briefly. Time disperses them again. In this sequence, individuality remains real at the level of experience, but materially it rests on borrowed cosmic substance. The unsettling force of this idea lies partly in how it alters human identity. A person may imagine life as something local, born entirely from Earth and belonging only to this one world. Yet the elemental foundation of that life begins elsewhere, in stars that live and die over immense spans. The body becomes a later chapter in a much older narrative. Even the capacity to think about the stars depends on atoms they once create. In that sense, the universe has become aware of itself using materials assembled in stellar cores and distributed by stellar death. The observer is made from the same cosmic history that is being observed. This does not make human life less meaningful. If anything, it deepens the meaning while also removing illusion. It reveals that life is not insulated from the wider universe. It is physically continuous with it. The blood depends on iron. The bones depend on calcium. The cells depend on carbon, oxygen, nitrogen, and other elements that are not primordial gifts of the early universe, but later products of stellar activity. The stars are therefore present not only overhead, but within. Their history is folded into metabolism, breath, and thought. The terror here is gentle but real. It lies in recognizing that what feels intimate and alive is built from matter, shaped in environments of immense heat, pressure, collapse, and explosion. Human life grows from cosmic violence without carrying its outward appearance. In the story of stellar secrets, this may be the most direct link between the distant sky and the inner human world. The stars are not just remote fires, they are the source of much of the matter from which worlds and bodies are made. Their life cycles enrich galaxies, their deaths release possibility, their remnants and debris become part of later systems. To exist as a living being on a rocky planet is therefore to stand inside the long aftermath of stellar creation and destruction. The calm of a human hand, the rhythm of breath, the iron moving in blood, and the minerals locked in bone all point backward to ancient stars. The universe hides this truth beneath familiarity, but once seen it cannot be unseen. The body is not merely beneath the cosmos. It is one of the forms the cosmos takes after stars have lived, died, and given their matter away. Beyond the lives and deaths of individual stars lies the long future of starlight itself, and this final scale may be the most unsettling of all. The stars that now fill the night with variety do not represent a permanent condition of the universe. They belong to an era. Massive blue stars burn out quickly. Ordinary stars like the Sun endure for billions of years, and the smallest red dwarfs persist for far longer than the current age of the cosmos. Yet even these long-lived stars are not eternal. The universe changes on timescales so immense that entire categories of familiar light eventually disappear. What now appears abundant and richly varied will one day become sparse, dim, and finally absent. The star-filled sky known to the present is therefore not the natural permanent face of reality. It is a temporary chapter in cosmic history, a bright interval between an earlier darkness and a possible later one. The smallest stars offer the longest resistance. Red dwarfs burn their hydrogen slowly because their lower mass produces lower core pressure and lower energy demand. They shine faintly, but they endure with extraordinary efficiency. Some are expected to last for trillions of years, far beyond the lifetimes of stars like the Sun. None have yet reached old age because the universe itself is too young. This fact alone shifts perspective. The vast future is not an abstraction detached from present astronomy. It is already written in the existence of stars whose full life histories have not yet had time to unfold. Long after brighter and larger stars vanish, red dwarfs may remain as the dominant sources of light in galaxies. Their dim red glow could define the distant future sky, a quieter universe lit not by grand brilliance, but by patient embers that refuse to go out. Yet this endurance does not prevent the larger decline. As star formation slows in galaxies and the available cold gas is used up or heated beyond easy collapse, fewer new stars are born. Existing stars continue according to their mass, but replacement diminishes. Over very long spans, the balance shifts from a cosmos rich in active stellar birth to one dominated by aging populations and remnants. White dwarfs accumulate. Neutron stars remain. Black holes persist. The bright short-lived giants disappear first, then the more ordinary stars, and at last even the red dwarfs exhaust their fuel. The details of extremely distant evolution include processes that remain partly theoretical, because they unfold far beyond direct observation. Yet the broad direction is supported by known stellar physics. Starlight is not endlessly renewable under present cosmological conditions. It is finite in duration, when measured across the life of the universe. This eventual thinning of light leads to one version of the future often called heat death, though the phrase describes a broader condition than temperature alone. In such a future, the universe continues to expand. Matter becomes more diluted on large scales, and accessible energy differences decline. Stars cease to form. Existing stars die. Galaxies grow dim. The cosmos moves toward a state in which structure remains but activity decreases. The future is not a single dramatic ending that arrives all at once. It is a long fading, a loss of brightness through attrition. This is perhaps more disturbing than catastrophe because it offers no final spectacle, only reduction. The night does not explode into darkness. It slowly becomes darkness by running out of stars. White dwarfs then cool still further, over spans vastly longer than the present cosmic age. They are expected to become black dwarfs, cold remnants that no longer radiate significant visible light. Neutron stars cool as well. Black holes may remain among the longest-lived large structures, though even they are not eternal if processes like Hawking radiation are considered over unimaginable timescales. Much about such extreme futures belongs to theoretical extrapolation, and it remains uncertain how all physical processes behave over durations so far beyond observation. Even so, the central picture is clear enough to carry emotional force. The current universe is young enough to be full of stars. The far future may not be. There are speculative ideas that suggest the story may not end in simple final darkness. Some cosmological models propose cycles, bounces, or new universes arising from conditions beyond the current cosmic horizon of certainty. In such ideas, future universes might produce fresh generations of stars. It remains uncertain whether any of these models describe physical reality. Present evidence does not establish a cosmic rebirth with confidence, but the existence of such ideas reflects an effort to think beyond the fading of current starlight. Whether the cosmos ends in permanent darkness or participates in larger cycles remains unresolved at the deepest level. What is known more securely is that the stars visible now are not permanent, and that their present abundance belongs to a specific age. The stars remain overhead in silence. Yet after their long history, the silence feels different. What first appears as a calm field of distant lights now carries a deeper weight. Each star holds a life shaped by gravity, fusion, time, and eventual change. Some swell into vast giants and lose themselves to instability. Some collapse into dense remnants that keep spinning in darkness. Some are torn apart near black holes. Some collide and scatter the elements that later become worlds, oceans, stone, and blood. Even the gentlest stars do not remain as they are forever. They brighten, age, shed their outer layers, and leave behind cooling remnants that drift into the future. The universe hides these processes behind stillness. From the ground, the sky seems patient and unchanged, yet every point of light belongs to a story of pressure and resistance, of matter transformed under conditions far beyond earthly experience. The stars are beautiful not because they are simple, but because they contain such immense histories within such quiet appearances. Their light reaches across great distances and across time itself, carrying news from places no human hand can touch. There is something peaceful in that distance. The stars do not hurry. Their changes unfold across spans so vast that even their violence belongs to a larger calm. They create, destroy, scatter, and fade. Yet the sky continues to open above the world each night with the same soft invitation to look upward. In that gentle view, the terrifying and the beautiful become part of one larger truth. The universe is severe, but it is also luminous. Its deepest secrets arrive not as noise, but as light. This gives the current sky a different meaning. It is not simply beautiful because stars shine. It is beautiful because they still shine now. Human beings live during a period when galaxies remain active, when stellar diversity still fills the universe, and when the products of earlier stellar generations have already made planets and life possible. The present is neither the beginning nor the end. It is a luminous middle. That fact can feel humbling and almost mournful, because it means the heavens now seen are temporary even on cosmic terms. The constellations will shift, the bright stars will die, the red dwarfs will linger, the remnants will cool, the great age of starlight will eventually pass. In this final sense, the deepest secret stars reveal is not only how they live or die, but that their entire era is limited. They are not permanent fixtures hung in darkness for all time. They are participants in a universe that changes even at the level of whether light-filled skies exist at all. To look upward now is therefore to witness something historically local in the life of the cosmos, an age when stars still burn across vast distances and make the universe feel inhabited by radiance. One day, by the logic of stellar evolution carried far enough, much of that radiance will be gone. The terror lies in the scale of the loss. The beauty lies in living during the bright interval before it happens.